A spoonful of hot sauce can make your heart race, your forehead sweat, your eyes water, and your mouth feel as though it has touched fire. Those are not the reactions we normally associate with good food. They are warning signals. Yet millions of people deliberately search for that sensation. They increase the heat, build tolerance, and eventually complain when a meal is not spicy enough. So why can the same burn feel unbearable to one person and deeply satisfying to another? The answer begins with a receptor on your nerves. But the real transformation happens much deeper inside the brain, where pain is measured, interpreted, predicted, and sometimes converted into pleasure. And contrary to a popular explanation, it is not simply because chili releases dopamine. The process is far more interesting. Let's follow the signal from the first bite. Spiciness is not detected by ordinary taste receptors in the same way as sweetness, saltiness, bitterness, sourness, or umami. Instead, chili peppers contain capsaicin, a molecule that activates pain-sensitive nerve endings in the mouth. On those nerves is an ion channel, called TRPV1. Under normal conditions, TRPV1 helps respond to potentially damaging heat, acidity, and inflammatory signals. Capsaicin fits into this channel and forces it open. Once the channel opens, electrically charged particles, especially sodium and calcium ions, flow into the nerve cell. That changes the voltage across the cell membrane. When the change becomes strong enough, the nerve fires an electrical impulse toward the brain. The chili does not carry fire into your mouth. It converts chemistry into electricity. The same receptor can respond to genuinely painful temperatures, which is why capsaicin and physical heat can produce such similar sensations. The discovery of TRPV1 as a heat-activated capsaicin receptor later contributed to David Julius receiving the 2021 Nobel Prize in Physiology or Medicine, but TRPV1 does not decide whether the sensation is frightening, enjoyable, or worth repeating. It only begins the message. After capsaicin activates nerve endings in the mouth, the signal travels mainly through branches of the trigeminal nerve. This is the large sensory system that carries information about touch, temperature, irritation, and pain from the face and mouth. The signal first enters processing centers in the brainstem. From there, it is relayed upward toward the thalamus, a region that helps direct sensory information to different parts of the cerebral cortex. Then the message spreads across a network. The somatosensory cortex helps identify where the burning is occurring and how intense it appears to be. The insula combines information from the mouth with signals coming from inside the body, including warmth, heartbeat, nausea, and emotional state. The anterior cingulate cortex contributes to attention and the unpleasant, demanding quality of pain, the feeling that something must be done about it. Brain imaging studies using capsaicin have also detected activity in regions associated with sensory perception, attention, movement preparation, and descending pain control. Pain is not produced by one pain center. It is assembled by a network. This explains something important. The physical signal entering the brain is only one part of the experience. The brain must still decide what that signal means. We often talk about pain as though it were a simple measurement. More signal means more pain. But human pain has several layers. One layer concerns intensity. How powerful is the burning? Another concerns location. Is it on the lips, tongue, throat, or entire mouth? A third concerns unpleasantness. How much do you dislike what is happening? These layers can change independently. Two people can receive similar capsaicin stimulation, but experience it very differently. One may describe the burn as intense but exciting. The other may experience the same intensity as threatening and intolerable. The anterior insula and cingulate regions are particularly important here because their responses are connected not only with the strength of painful stimulation, but also with its emotional significance and unpleasantness. This is why enjoying spicy food does not necessarily mean a person feels no pain. They may feel the burn clearly. What changes is their evaluation of it. Spice lovers do not always silence the alarm. They learn to disagree with it. And one of the strongest forces shaping that evaluation is expectation. Before hot sauce reaches your tongue, your brain is already making predictions. It uses the color of the sauce, its smell, the restaurant, previous experiences, and even the warning printed on the bottle. Those predictions can change what happens next. In a 2024 brain imaging study, researchers gave participants hot sauces while manipulating the information that created expectations about them. People who liked spicy food showed stronger pleasure-related responses when they expected a favorable experience. People who disliked it showed stronger activity connected with pain and negative emotion when their expectations were unfavorable. The physical stimulus mattered, but it was not acting alone. Expectation altered both the reported experience and the brain's response. Imagine two people taking the same bite. One thinks, "This will be exciting." The other thinks, "This is going to hurt." Those thoughts do not magically remove capsaicin from the food, but they can influence how attention, emotion, and reward systems interpret the incoming signal. This is one reason controlled pain feels different from unexpected pain. When you choose the sauce, know why the burning is happening, and understand that it will end. The brain has more information and more control. Research using capsaicin-based pain models shows that controllability can alter activity in brain regions involved in pain evaluation and cognitive processing. The same alarm can feel different when your hand is on the switch. The first few bites of spicy food may not make the burn weaker. They can briefly make it stronger. When capsaicin is repeatedly applied at short intervals, nerve responses may become sensitized. Each exposure can feel increasingly intense because the sensory system remains activated. But after longer and repeated exposure patterns, the opposite can occur. The system becomes less responsive. This is called desensitization. Calcium entering through activated TRPV1 channels begins processes that temporarily reduce the nerve's ability to keep responding at the same strength. With regular exposure, frequent chili consumers often report less oral burning than infrequent consumers. Controlled studies have produced measurable reductions in perceived burn after repeated low-dose exposure. So tolerance is not merely a demonstration of willpower. Part of it happens in the sensory nerves themselves. But desensitization does not completely explain love. A weaker alarm might make spicy food easier to tolerate, but it does not automatically make it pleasurable. For pleasure to develop, the sensation must also become associated with something rewarding. A common internet explanation says that capsaicin causes pain releases endorphins and dopamine, and those chemicals create an addictive high. That explanation is too simple. Pain regulation can involve the body's natural opioid systems, and dopamine participates in motivation, learning, and reward. But human enjoyment of spicy food cannot be reduced to one automatic chemical release. A stronger explanation combines four processes. First, desensitization makes the burn more manageable. Second, prediction reduces uncertainty. The brain knows what is happening. Third, control turns the experience into a chosen challenge rather than an imposed threat. And fourth, learning connects the burn with positive rewards: flavor, satisfaction, family meals, social approval, or the pride of handling a hotter level. Psychologists sometimes describe enjoyment of safe, controlled discomfort as benign masochism. The same broad principle can appear when people enjoy horror films, exhausting exercise, sour candy, saunas, or roller coasters. The body produces an alarm-like reaction, while higher brain systems understand that the situation is limited and controlled. The pleasure may not come from pain alone. It may come from successfully mastering the pain. Eventually, the brain begins predicting not only the burn, but everything surrounding it: the aroma of the dish, the expected flavor, and the relief and satisfaction that follow. The warning becomes part of the reward. Spicy food preference is shaped by several systems at once. People differ in receptor sensitivity, previous exposure, culture, personality, expectations, and the memories attached to particular foods. Someone raised around chili may learn its signals early and connect them with comfort. Another person may discover spicy food later and enjoy its challenge. A sensation seeker may prefer stronger stimulation, while someone highly sensitive to bodily signals may find the same meal overwhelming. Even experienced spice lovers usually have a preferred zone. Below it, the food feels dull. Inside it, the burn adds excitement and intensity. Above it, pain captures too much attention and hides the rest of the meal. That limit can move with experience, but it rarely disappears. So why do humans love eating spicy foods? Capsaicin opens heat-sensitive TRPV1 channels and generates a genuine electrical pain signal. That signal travels through the trigeminal system into a brain network that measures its location, intensity, unpleasantness, and meaning. Repeated exposure can reduce nerve sensitivity. Expectations can change brain processing. Control makes the sensation feel safer. and learning connects the burn with flavor, memory, achievement, and reward. Spice lovers are not immune to the warning. Their brains have simply learned a different interpretation. What once meant only danger can gradually come to mean anticipation, excitement, comfort, and pleasure. So the next time a chili makes your eyes water while your hand reaches for another bite, remember, the pepper activated the alarm, but your brain decided whether to run from it or enjoy the ride.